In the last two slides of this lecture, we introduced the concept of colligative properties. When you mix a solute into a solvent and form a solution, you would expect the properties of the solution to differ from these of the solvent and depend on the amount of solute and on its properties. In contrast with this expectation, a number of properties, called colligative properties, actually show remarkable similarities to each other in that they depend only on the amount of solute and not on the properties of the solute. Some of these properties, however, do depend on the property of the solvent, as one would expect. The simplest example of colligative properties is the lowering of the solvent vapor pressure, observed when adding a solute to a solvent. Using Raoult's law for the almost pure solvent, the difference between the vapor pressure of the pure solvent, Pa star, and the partial vapor pressure of the solvent above the solution, Pa, is written as Pa star minus Pa star XAL, which is equal to Pa star times 1 minus XAL, which we can write as XBL times Pa star. So we conclude that the partial vapor pressure of the solvent above the solution is depressed below the vapor pressure of the pure solvent by an amount that is proportional to the amount of solute in solution. Another example of colligative properties is the boiling point elevation, delta B, which we define as the boiling point of the solvent in solution, TBA, minus the boiling point of the pure solvent, TBA star. While the derivation is not shown here, it results in delta TB equals KB times B sub B, where KB is called ebullioscopic constant for the solvent, and B sub B is the molality of the solute. The ebullioscopic constant is the product of the molar mass of the solvent, the gas constant, the square of the solvent boiling temperature, divided by the standard enthalpy change for vaporization of the solvent. This relationship indicates that the boiling temperature of the solvent in solution is increased above the boiling temperature of the pure solvent by an amount that is proportional to the amount of solute and dependent on the properties of the solvent alone. The same kind of relationship can be obtained for delta Tf, the difference between the freezing point of the pure solvent and the freezing point of the solvent in solution. In this case, the constant of proportionality is called the solvent cryoscopic constant, K sub f. In parallel to K sub b, K sub f is the product of the molar mass of the solvent, the gas constant, the square of the solvent melting temperature divided XBL by the standard enthalpy change for melting of the solvent. Note that in contrast to the boiling temperature, the melting temperature of the solvent decreases when the solute concentration increases. This is obviously of much practical importance, as it allows us to predict that salt added on the roads in the winter leads to a decrease in the temperature at which the roads will freeze. It also explains the modus operandi behind the soldering process. Finally, osmotic pressure, the topic of our next lecture, is one of the most important colligative properties in the life sciences. We will show that the osmotic pressure, pi, is proportional to the number of moles of solute B in an expression that looks very similar to that of the Al gas law. All these properties derive from the fact that μAl, the chemical potential of the solvent in solution, is depressed below that of the pure solvent by an amount that, for dilute solution of B, is proportional to the mole fraction of solute B. Rather than justifying quantitatively the existence of a freezing point depression and a boiling point elevation for the solvent in solution, we will provide a qualitative description of these phenomena using the same plot of chemical potential versus temperature as we introduced in earlier lectures. On such a plot, we see the decrease in solvent chemical potential with increasing temperature for all three phases of the solvent. The slope of solvent chemical potential versus temperature increases from solid to liquid to vapor, reflecting the increase in molar entropy from solid to liquid to vapor. Where the solvent chemical potential curve for the solid intersects that of the liquid, we observe the melting or fusion temperature of the pure solvent. Similarly, where the chemical potential curve for the liquid intersects that of the vapor, we observe the boiling or vaporization temperature of the pure solvent. We now examine how this diagram needs to be modified for solution of a solute B in solvent A. The equations provided on the preceding page were derived on the basis of three assumptions. First, we assume that the solute is non-volatile. This implies that the vapor phase remains pure solvent even after solute and solvent are mixed in the liquid phase. It also implies that μAV, the chemical potential of A in the vapor phase above the solution, is the same as μA star V, the chemical potential of A in the vapor phase above the pure solvent. Second, we assume that the solute B does not crystallize with the solvent to make a mixed crystal phase. If the solvent remains pure as it crystallizes from solution, then its chemical potential remains identical to that of the pure solvent. Third, we assume that the solute is present in small concentration. Under such condition, the solvent is almost pure and obeys Raoult's law. So its chemical potential can be written as μAL equal to μA star L plus RT times the natural log of XAL, which can be recast for XAL values close to 1 as μA star L minus μAL equal to RT XBL. This obviously implies that the chemical potential of the solvent in solution is depressed below that of the pure solvent by an amount proportional to the product RT-XBL. As a result, the freezing point of the solvent is depressed from TF star to TF, and the boiling temperature of the solvent is raised from TB star to TB. Note that the boiling point elevation and the melting point depression are both proportional to the mole fraction of solute in solution.